Hi there, I'm back again with another video. This time I want to talk about catenary systems. Now, if you're anything like me, you might have been wandering around the sticks and looked at electrical cables hanging from pylons. Now, I used to wonder, are they parabolic curves they make as they sag between the pylons? And I used to think, wow, they're quite beautiful curves and they're just hanging by their own weight. And it turns out they're not actually parabolic. They thought, the mathematicians back in the day thought they were for a long time. But in 1691, your man Leibniz came out and told us they weren't parabolic. They're actually what we call catenary curves. So where any rope that hangs between 2 points, it's not parabolic, it's catenary. And it was Leibniz who gave it that name. You know, another giant of mathematics. He come up with calculus and all sorts of stuff alongside Newton. So today I want to take a look at how they derive the hyperbolic function to represent the catenary curve. So with that said, let's dive right in. First, like anything in maths, we need to model it. So I've done a quasi-catenary curve here. The points to note: the only forces operating on this rope will be tension and its own weight. So I've got horizontal tension there at the lowest point. The tension is a tangent function to the rope at any point. So at the lowest point, the tension acting to the left in this case is horizontal, so that's good. And at this point, a little bit further along the rope, I've moved an arc length S. Okay, so we can imagine this to be a tiny little amount along the length, and then we're going to add up all these little lengths to get the final function. So this point here, I've got another tension force pulling the other way, going up that way, and if I resolve these forces, I get me classic T sine theta and T cosine theta. So that's your AS level vector resolution. I also have the weight coming down, and I'm calling my weight USG. Now why have I chosen, it's normally MG, but why have I chosen these? Well, it's to keep the maths nice and make sure we get this S involved in our subsequent equations. So what is U? U is the mass per unit length, so the amount of mass per some amount of length, and S is the arc length. So you multiply these two together and you just get mass, which would, mg would give us the force of the weight. Okay, so that's all excellent. Now the next thing we can do is equate the forces. Now I can see T sine theta is the component of tension that acts vertically upwards, and obviously because nothing's moving in this system, everything's in equilibrium, therefore all the forces are balanced. So I can say my T sine theta must equal USG, and that's there. So that's equating the vertical components. Now looking at the horizontal components, I've got me horizontal component of tension acting to the right there, that's T cos theta. And that must equal the tension at the lowest point, which is T0, and that's here. Alright, so that's how we begin, that's how we set the system up, ready to derive the ultimate equation. Now the next part, I can take these two equations and divide them. It eliminates the T and gives me a tan theta equals USG over T naught. Great! Now the next little trick, because T naught is just tension, the horizontal component of tension is constant at any point in the rope. And U is the mass per unit length, that's a constant, and gravity is a constant. We're not moving to any other planets or going into orbit or anything, so these are all constant terms. I can just call that A. Now if I substitute A back into here, I end up with tan theta equals S over A. Now tan theta is opposite over adjacent, and if I look at this triangle here and think of it in the Cartesian plane, I get a change in y divided by a change in x. So opposite over adjacent is dy over dx. And that's what I've written there. Okay, all very good up to now. Okay, so we just established that dy over dx, or the derivative of y, is s over a. Now, it would be nice if I could get some x's on one of the sides. So what I'm going to do now is just differentiate both sides. So if I do that, I get my second derivative, and I'm going to have to use implicit differentiation, and we'll differentiate y with respect to s, and so the s goes to a 1, I get 1 over a times ds over dx. That's implicit differentiation. So I end up with this term here, or this equation, and the interesting thing here is that ds over dx, well, what is that? Well, that's a change in arc length for a small change in x. So as I move along the x-axis, I get a little increase in arc length. So there's actually a formula for that, which is derived in another class. But ds over dx equals this. It's 1 plus the square of the derivative of y, all square rooted. Okay, so sometimes they call this y prime. It's a bit easier. I always think of that as the American way of saying it, but it does simplify stuff a lot. So yeah, we've got this equation here representing ds over dx, and of course I can substitute that into there. So that's all I'm going to do for this bit. The second derivative equals 1 over a times ds over dx, which is this. Now, because I'm not very smart, I can't integrate second derivatives. So what I want to do is substitute p in as the first derivative. All right, and that'll simplify things a lot, especially for someone like me. So if I do the substitution, and the second derivative becomes dp by dx, that's nice, and that part in the brackets there, the derivative squared, just becomes p squared. So I get dp over dx equals 1 over a square root of all 1 plus p squared. Now, this is a differential equation when you're in your A-level maths. I think it starts in year 13. We can solve this by separating the variables. So what I do, I got all the p's on one side and everything else on the other side. And I end up with, 1 over p squared all square rooted. dp with a little change in p, and now 1 over a dx. Now if I integrate both sides of this, the right side's easy. That's just going to become x over a, if I integrate it with respect to x, and if I integrate the other side with respect to p. Now that function is not so simple, and I had to look it up. But you actually end up with arc shine p. Right? You can look that up. It's a known integral that you can do. So it comes out as arc sine or arc shine p. Well, this is hyperbolic sine, but it's the inverse part of it. Okay, so you'll have to just take my word for that. That's another derivation you have to look at. So what I want to do is take that to the other side, and it becomes regular shine x over a. So p equals shine x over a. That's great. But remember before I said p was the first derivative. So I'm going to swap p back for that. I get dy over dx, or y prime, equals shine x over a. Lovely. And again, I'm going to have to integrate both sides. It's basically like integrating this twice kind of thing. So to integrate both sides of that, again, this is another known integral. I end up with y equals a cosh x over a plus c. Now the final little trick is to fix the low point at a, or the low point on my chart, on my graph up here, is when x equals 0. So if I come down here and make x equals 0, the cosh of 0 is 1. And if I make y equal to a at that point when x is 0, c becomes 0. So I can just eliminate that constant of integration. And we ultimately end up with this equation here where y equals a cos x over a. So if I put any value of x in, I can work out any point at y, which will be where the bottom of the curve is a units above the x-axis, or above the origin. Okay, and that's absolutely fantastic. The equation for any catenary curve, or any cable hanging by its own weight, like a chain fence or a necklace or anything like that. So that's absolutely amazing. I love it. Okay, thanks for watching. See you later.